Okay, summer 2020 midterm walkthrough, take 3. Hopefully the audio records this time. Okay. Okay. Let's do this test for the third time. This is lots of fun. Okay, report the following arithmetic result with the correct number of sig figs. So basically, we're adding 3 things together, right? We do have to add these 2 together first if we want, but we really don't have to since it's being all added, right? It doesn't matter. So let's do our first thing we have to add together, which figure out what it is. First is division. We have 1, 2, 3, 4, 5 sig figs divided by 1, 2, 3, 4, 5, 6, 7 sig figs. So this has 5 sig figs. This is the math. So that means 5 sig figs. This is all that is significant for that number. So 137.50, where 0 is our first uncertain number, 3, 8, 6, 6, etc., etc. Let's look at the next one. Well, we have to do the addition on top before we can figure out what the sig figs is from the division. So let's do the addition. So how many decimal places to the right of the decimal point do we have here? 1, 2, 3, 4, 5. This one has 2. This one has 4. Okay, well 2 is going to set the where our error is. So we can only have 2 decimal places to the right of the decimal point. So that means our number up top will have 4 sig figs. Down below we will have 5, which means this math overall can only have 4 sig figs. So here's the complete math, can only have 4 sig figs. So that will take us to the ones place. So we have 349.893.115, etc., where our first uncertainty is in the ones point. And then lastly, we have the log of 2.72452, which is 6 sig figs. So it's taking a logarithm, which means we have to have 6 sig figs after the decimal point. So 1, 2, 3, 4, 5, 6. It's a 0. So 0.435290000029, where our uncertainty is not 0. So where's our largest uncertainty? It's in the ones place. So when we add this all together, our uncertainty has to be in the ones place. So the answer is C. Okay, so now we have 3 things we're multiplying together. Of course, these are in brackets. You can do them first, but you can do them all together at the same time. That's up to you. You'll get the same answer. So let's figure out what these numbers are we're multiplying towards each other, because once again, the smallest number of sig figs is what dictates how many sig figs there will be in the answer. So the first one is we have 5 sig figs divided by 6 sig figs, which means whatever this is, it can only have 5 sig figs. Okay, what about this one? Well, we have this math up top we have to do first, subtraction. So we have 2 past the decimal place, 2 past the decimal place, which means we can only keep 2 past the decimal place, which means our numerator has 4 sig figs. Our denominator has 1, 2, 3, 4, 5, but when we do the math, this can only have 4 sig figs. And then lastly, let's figure out this one. We have to the 4th decimal place. Here we have to the 5th decimal place, so we can only keep to the 4th decimal place. So where's our math here? To the 4th decimal place right there, which means this has 5 sig figs in it as well. Which means when we're done with our math can only have a maximum of 4 significant figures, which puts us in the tens place. That 5 will cause it to round up. Our answer is 56720. Report the following arithmetic result with the correct number of sig figs. Here we're doing addition again, addition of these 3 numbers. So we have to figure out where our uncertainty lies, and we have to report the largest one when we add them together. So let's do our first term first. So let's add these 2 together. Here we have 3 past the decimal place. We have 1, which means our uncertainty is 1. So there are 4 sig figs in the numerator of this. In the denominator, we have 1, 2, 3, 4, 5, 6, 7. Doesn't matter if it's 7 or 8. 4 still wins. So for this overall number, which is right here, we can only have 4 sig figs, which puts us in the tens place. So 1, 2, 1, 1. 7.2405, etc. Okay, the next number is pretty concise. It's just this number. So 7391, underline the 1. And then we have the logarithm of something with 6 sig figs, which means we have to keep 6 sig figs after the decimal place. So here's our logarithm of that, 2.389773. That's 6 sig figs after the decimal place, 67. When we add all ours together, the largest uncertainty is in the tens place. We can only keep to the tens place. So 19510 is our answer. For the ruler below, how many sig figs should be reported for the measurement of the bar? Okay, well, let's measure the bar. So I have 0.067, and then it's greater than the 2, but less than the 3, so we'll call it a 2. And the next one I have to guess, I'm going to guess a 6. And this one is going to be 0.062. It's greater than the 1, less than the 2, so it's a 1. And then I'm going to guess, I don't know, 5. Doesn't matter what number you guess there. It'll always come up with the same number. Got a 1, got a 1, got a 5, 0, 0, 5, 1, 1. That's 3 sig figs. Boom. Select the definition of significant figures. Select 1. All the certain digits that follow the decimal point. That's false. That's not good. Right? Wrong. All the certain digits that precede the decimal point. Once again, crazy talk. All the certain digits plus the first uncertain digit. Yes, this is our definition of significant figure. All the certain digits plus the first uncertain digit. D, all the certain digits plus 2 uncertain digits. Okay, I'm going a little overboard with that one. Okay, all the certain digits and no uncertain digits. No, that's not how it works at all. Right, all certain digits plus the first uncertain digit. Report the following arithmetic result with the correct number of sig figs. Select 1. So let's start with what the answer is, the units of the answer, which is 10 to the minus third. Let's put all of these in 10 to the minus third and add them together. And let's start on the right and work our way to the left, since this one already has the correct number of sig figs. So 3.48337 times 10 to the minus third. Okay, the next one, right? That's 10 to the fourth, so that decimal point will move there. So 0.545. Notice how I'm lining them up properly. 374. Right, also times 10 to the minus third. 10 to the minus fifth, so this decimal place will move over twice. 0.0464345 times 10 to the minus third. And last we have 10 to the sixth. This will go to the fifth, the fourth, and the third. So 0.00934. Now if we look down these alleys carefully, right, we can see our largest uncertainty ends right here with this 9.34 from this number. So that's really going to set our error. So since it's in 10 to the third, it's going to be at the first, second, third, fourth, fifth decimal place. 1, 2, 3, 4, 5. The answer is C. Okay? So it winds up, this number is what sets the error. Right? It has the first, right, uncertain digit. It has the largest uncertain digit. Okay, a student calculates the average standard deviation of unknown gas as negative 44.77433945 plus or minus 0.04366435. The dial for the thermometer shown on the right. How should the answer be reported? Step 1. Report the error with one significant figure unless it begins with a 1 or 2. Okay, let's do that. Step 2. Report the answer so it matches the precision of your error. Step 3. Are you doing better than the device? Well, let's find out what the error of our device is. Well, we have the tens place is denoted with indicators. So aren't the ones place, right? Each one of these is a ones. So each one of the tens place and the ones place are certain, right? We know that the tens and the ones are certain. Now the first uncertainty is the next step below 1, which is 0.1, right? That's our first uncertainty. And a good way to do that is just picking any dot and getting the measurement. Okay, so let's take that measurement. It's between minus 30 and minus 40, so that would be minus 30, 2, and we'll call it, I don't know, 3, right? Because we're 1/3 the way, maybe it's 2, right? That's our uncertain digit. So we can only read it to plus or minus 0.1. So what's bigger, plus or minus 0.1 or plus or minus 0.04? Well, plus or minus 0.1 is bigger, so we can't use this, right? We have to make the number match, and we'll have to round it. A student calculates the average and standard deviation for pH of an unknown acid as 8.3736293 plus or minus 0.0295765. The pH meter shows 2 decimal places. How should the result be represented? Well, step 1, represent the error with one significant figure unless it begins with a 1 or 2. It begins with a 2. So 0.29, that 5 is going to have it round up. So it'll be 0.030. No longer begins with a 1 or 2. So 0.03 plus or minus. Rule 2, we have to have this number match. So 8.37. Rule 3, are we doing better than the instrument? The instrument error is plus or minus 0.01. What's bigger? 0.03 or 0.01? 0.03 is bigger. Our answer is B. A student calculates the average standard deviation for pH of an unknown acid or base is 2.636456 plus or minus 0.58264. The pH meter shows 1 decimal place. How should you report the error? Rule 1, report the error with one significant figure unless it begins with a 1 or 2. It does not. It begins with 5, which will round to 6 because of the 8 next to it. Rule 2, the answer must match the error. So 2.6. Rule 3, are we doing better than the instrument? The instrument reads to 1 decimal place, so the instrument is 0.1. What's bigger, 0.6 or 0.1? 0.6 is bigger, so the answer is B. A student measures the pH of an unknown solution 3 times and obtains the average of 6.2731 and a standard deviation of 0. The pH meter is shown below. How can you report this result? Well, you can't have a standard deviation of 0, right? So at the worst, you have to report the error of the instrument. So 0.001 plus or minus, now this must match, 6273. Right. An acid has a Ka value of 7.0084 times 10 to the minus 9. The corresponding value for pKa is shown on your calculator as 8.1543811. Report the pKa with the correct number of sig figs. Okay, remember, we have a Ka value, which is a normal number, and I'm asking for the logarithm of that number. So we have 1, 2, 3, 4, 5 sig figs, which means if we're taking a logarithm, we have to have 5. Our sig figs are only counted after the decimal place. So we need 1, 2, 3, 4, 5. So out to that 8. So that would be Bravo, right? We have 1, 2, 3, 4, 5 significant, or 5 decimal places, 5 significant figures after that decimal place. The pKa of an acid is reported as 10.58. The corresponding value for Ka shown in your calculator is 2.630267 times 10 to the minus 11th. Report this concentration with the correct number of sig figs. Okay, once again, a pKa, this is a logarithm here. So logarithm, the significant figures are only counted after the decimal place, which means this only has 2 sig figs, which means we have to report this number with 2 sig figs, right? There's 2 sig figs. Right, that 3 won't get it to round. A student measures the mass of a precipitate of 6 trials using the balance shown below and calculates the average as 47.73943835 grams and the sample standard deviation of 0.00986493. How should the student report his results for report 1? Well, once again, Rule 1, report the error with 1 significant figure. Okay, so this is going to be 0.009, but that 8 will have it round up. So, and now it begins with a 1, which means we have to keep 2. Rule 2, this must match our error. So 47.7394 739. Rule 3, are we doing better than the instrument? The instrument is plus or minus 0.0001, right, because 4 decimal places. What's bigger, 0.01 or 0.0001? It's 0.01, answer is B. You measure the mass of the sample of penicillin G using a balance that has 4 decimal places and get the following masses. 2.6632, 2.6631, 2.6632. You calculate the number of moles of each sample using a calculator. The calculation for the first sample and calculator output are as follows. The average number of moles and sample standard deviation for the 3 measurements shows up on your calculator as 0.00796405152 plus or minus 0.00. So let's say 0.000001727. How should you report this result? Rule 1: report the answer report the error with one significant figure. This begins with a 1 or 2. This begins with a 1 or 2, so plus or minus, right? Looks like we have 6 zeros. 1, 2, 3, 4, 5, 6, and then the 1, 7. So now we have to report our answer with that same level of precision. Rule 2, right? 0.00796402, because that 5 will have it round, right? Rule 3, are we reporting it to a higher precision than we are allowed to because of the instruments used? Well, let's find out what the precision of our instruments are used. Here we have 5 significant figures. Here we have 4 significant figures, which means our answer can have 1, 2, 3, 4 significant figures, which is to the 6th decimal place, which means our error in our instrument is 1, 2, 3, 4, 5, 6. So what's bigger, right? 5 zeros and a 1 or 6 zeros and a 1? Well, 5 zeros and a 1 wins, right? 0.000001. And so then this has to match 0.0079, right, 64, right? And so that dictates what our answer should be. Cool. You measure the massing sample of 3 samples of penicillin G using a balance and has 4 decimal places. You get the following masses: 79.3811, 79.7386, 79.1189. You calculate the number of moles of each sample using a calculator, and the calculation for the first sample and calculator output are 79.3811 grams times 1 mole over 334.4 grams for the answer. The average number of moles for the sample standard deviation and 3 aliquots show up as 0.23748444976 plus or minus 0.008342105. How do you represent the result? Well, rule number 1, report the error with one significant figure unless it begins with a 1 or 2. Does not begin with a 1 or 2, so we have plus or minus 0.0008, so 0.2375. Okay, so I mean, rule 2, you have to report the answer to the same precision, so 0.2375. Rule 3, are you doing better than the instrument? Here we have 6 sig figs. Here we have 6 sig figs. Here we have 4. So we can only have 4. So we can, our error in our instrument is plus or minus 0.0001. So what's bigger, 0.0001 or 0.0008? 0.0008 is bigger, so that dictates our answer. Student measures the precipitate using 3 different balances, one that show 1, 3, and 5 decimal places, and record the following values. 0.2, 0.193, and 0.18536. The average is calculated, right? And so our answer, right, is dictated because right here we're reporting all grams and our answer is in grams, right? Or you can just say, hey, we have 1 sig fig, right? So we have to track 1 sig fig, or we can say the limit of our instrument is going to be that 0.1, right, as well, this decimal place. Both arguments work. Neither are more correct than the other, so the answer is 0.2. You purchase 2 volumetric pipettes. One pipette is 10.00 milliliter, and one is 20.00 milliliter pipette. You do not care which pipette you use for your experiment. You only require the pipette with the highest accuracy. You obtain some water and measure the water's temperature. Pipette the water into vials, weigh the vial in water, calculate the volume based on the density of water. This is just exactly as you did in experiment 1. Determine the average volume of the 10 ml pipette to be 9 plus or minus 1 ml, and the average of the 20 ml pipette to be 19 plus or minus 4 mils. Which pipette should you choose for your experiment? So if you did 1 over 9 and 4 over 19 to calculate the standard deviation, that's precision. That's going to be the wrong measurement to do. Okay, so what you have to do is you need to calculate you have to calculate the precision for the 10 mil and the 20 mil, right? And so that's going to be what the volume should be minus what it is, right, divided by what it is, times 100%. Okay, and here you'll see it's 1 over 10 times 100%, or 10% error. And here you're going to see it's 1 over 20, or 5% error. So this one has more accuracy than the other. So the answer is A. Because 1 over 20 is smaller than 1 over 10, right? Select all statements that are false. Select 1 to 5 answers. A given systematic error shifts results in both directions. No, systematic error shifts it in one direction, so this is false. Systematic errors can, in theory, be identified. Yeah, we use a standard, right? You can detect the shrunken ruler using a standard. We can identify it. Systematic errors always have a Gaussian distribution. No, random errors have a Gaussian distribution. Repetition of measurements reveal the random error. Yeah, the more times you measure something, the more information you get on its standard deviation and the random error. In fact, the more measurements you take, the smaller your error in that measurement gets. So yes, true. Should mark this true. Random errors affect accuracy. No, random errors affect precision, right? So false. So those 3 are false. After 49 trials, the average mass delivered from a pipette is 146 grams with a standard deviation of 25. If you perform a 50th trial, what is the probability your mass will be between 71 and 121? Select one answer. Okay, well, let's graph it. So I have the average is 146. And I'm interested in numbers smaller than it. So let's do the math. 146 minus 25 is 121. So at 1 standard deviation is 121. And if I minus another 25 from that, right, that goes to 11, so 6, and that's 11, so 96. Is that right? Oh my gosh, I can't even do simple math anymore. 11, that went to a 1, 9, 10, 11. Yeah, oh my gosh. That's how I lose it. 96, and then 25 again for 71. Okay, so 121 is 1 standard deviation away, right? 96 is 2 standard deviations away, right? And 71 is 3 standard deviations away. Let me just erase this and draw this a little bit better. Wow. All my years of art school wasted. Okay, and what we're interested in, right, is between 71 and 121. So we want to know how much is in this area. Okay, so instead of calculating that, let's calculate some other numbers. So here's 1 standard deviation, 2 standard deviations, 3 standard deviations on the other side. Let's do this the mathematically easiest way. So if I wanted to figure out 3 standard deviations away, which would be between 71 and whatever 3 sigma is on this side. That would be 99.7% of what we have, right? So that would give us all that area under the curve. So I only want up to 1 standard deviation though. So I want to minus 1 standard deviation away. Well, what's 1 standard deviation away? 68%, right? So if we do that, we got 0.7, 9 from 8 is 1, we got 31%. But that gives us not only this area that we want, but it also gives us this area because it's, remember, it's symmetrical on both sides. So basically we've taken all of it and we've cleaved out that 68% in the middle. But I only want one of these sides. So let's divide that 31.7. Let's divide it by 2. So, right, 2 goes into this, right, 3 times, roughly. And then goes into this, what about 15.5, so that's an 8. Right, so around 15.8. So half of 31.7, so 15.8. So where's 15.8? D. Right. The other way you could do it is actually take 99.7 divided by 2, and then minus 68 divided by 2. That's easier using the big numbers. It really doesn't matter. Why? Let's see. Oops. Oh, that's interesting. Didn't mean to do that. Where were we? Somewhere in here somewhere. I just wanted red ink. Okay. Why do we try to have as many trials as we can for an experiment? Select one. More trials minimizes the standard deviation. No. Your standard deviation, whatever. So let's say you take a standard deviation with 3 measurements. Okay. And let's say you add in a new point. Could your standard deviation get bigger? Yeah, it could. So obviously it's not going to minimize the standard deviation. Your real standard deviation could be larger. So this is false. Right? It looks good, but it's not. It doesn't minimize your standard deviation. More trials lowers the percent error. No, more trials does not make you more accurate. More trials lowers the percent RSD. No, because if your standard deviation has to get bigger, your percent RSD will get bigger, so also false. More trials lowers the error in your standard deviation. Yes, you know your standard deviation better. Maybe your standard deviation gets bigger, maybe it gets smaller, but you know it with less error, right? Because remember, an n gave us n of 3 gave us a 50% error, and then when we got up to n's of like 100, we still had like, I don't know, 3 or 7% error or something like that. We just knew our error better. Remember, that goes back to our delta S over sigma measurement, right? That's exactly what that is. We just know what it is better. More trials give us correct answers. That's just poor answer making on my part. So the answer is D. How should you report your average and its corresponding standard deviation? Select one. The average and standard deviation should have the same number of significant figures and the same number of decimal places. That's awful. I don't know how I came up with that. The average should be reported with 1 significant figure unless it begins with 1 or 2, then it should be reported with 2. This looks great, but remember, it's the error that should be reported with 1 significant figure, right? The average then should match that precision, so false. The average should be reported to the same decimal place or precision as the standard deviation. This is true, right? That's rule number 2. The average and standard deviation should have the same number of significant figures. Absolutely not. None of these answers are correct. No, because we have one that is correct. 22. Select all statements that are true. The percent error provides information on the relative precision of one measurement to another. No, percent error says is relative accuracy, and relative precision is measured with % RSD. So this is a big false. Systematic error contributes to the % error. Absolutely true. Random error is revealed with the repetition of measurements. Yes, right? The more measurements you take, the more you know about the random error. That's it. Doesn't mean it gets bigger, doesn't mean it gets smaller. You just know more about it. The systematic error can be revealed. Pardon me. Whew. The systematic error can sometimes be. The systematic error can sometimes be revealed by using a standard. Yeah, right. If you have a shrunken measuring tape, that'll reveal it. So yes, true. Once again, random errors reflect statistical fluctuations associated with measurement. Yes, true. So those 4 are true. You perform standardization and titration to determine the molecular weight of an unknown acid. The calculation for representative trial is shown below. When applying the third rule of reporting errors, what should we consider the instrument error? Select one. Well, everything here is multiplication and division, so what rules this is simply what has the lowest number of sig figs. Here I have 4. Here I have 5. Remember, 1 mole is infinite. This 1 is infinite. Here I have 5, which means this answer here can only have 4 sig figs as denoted by this. That goes down to the bottom, so that's 4 sig figs. Here's 4 sig figs. 4 sig figs, which means my answer can only have 4 sig figs. So my uncertainty is in that 4. If that 4 can go up or down by 1 because it's uncertain, there's my uncertainty. What is the correct reading for the period on the right? Well, it's between 43 and 44, or 0.43, 0.44, so it's 0.43. And then what? There's a line, it's roughly 7. I'm going to call it 7, 0. Right, because the first number I had to guess at is that 0, so that could be a 1 or 2, or it could go down to 4, 3. This could also be 6, 9, right? Go up or down. So let's see. It has to be greater than 43, so all those are out. It cannot be this one because you need one more decimal place, right? Because that 7 or 6 would be certain. So that's wrong. So the only one that could actually has the correct number of sig figs is this answer. And so yeah, it could be that one too. You buy 2 identical thermometers and measure the temperature of a lake. You place the thermometers in the lake side by side and wait for 1 hour. After 1 hour, you record the temperature from both thermometers once every 15 seconds for a total of 50 measurements of each. Thermometer A reads 30 point plus or minus 3, and thermometer B reads 40 plus or minus 4. Select one. We're looking at accuracy and precision. So what can we say about these two? Right? We have, we have thermometer A and B, and we can calculate the standard deviation for thermometer A and thermometer B, and we can see that they both equal 1 over 10, right? So they both have the same percent standard deviation, which means they have the same precision, right? Now, what about their accuracy? Well, we have to know what the number is versus what the real number of the temperature of the lake is given. It's not given, so you cannot calculate, right? You cannot calculate the accuracy. Accuracy cannot be calculated. Okay, so let's read through these. Thermometer A is more accurate and more precise. Nope. Thermometer B is more accurate and precise. Nope. Thermometer A is more accurate but less precise, right? We can't talk about accuracy. Thermometer B is more accurate but less precise. No, we can't talk about accuracy. Thermometer A is more precise but less accurate. No, still can't talk about accuracy. Thermometer B is more precise and less accurate. No, can't talk about accuracy. Thermometer A is more accurate than thermometer B, but precision can't be determined. Nope, can't talk about accuracy. Thermometer B is more accurate than thermometer A, but precision can't be determined. Nope, can't talk about accuracy. Thermometer A is more precise than thermometer B. We know that's false, but accuracy cannot be determined. So the accuracy component is correct, but it is not precise, more precise. Thermometer B is more precise than thermometer A. False, but the accuracy cannot be determined. So the accuracy component is correct, but now the precision's off. The thermometer and A have the same precision and accuracy. Nope, can't talk about accuracy. Thermometer A and B have the same accuracy, but precision can't be determined. No, we can't. It's the opposite. We can't determine accuracy. Thermometer A and B have the same precision, perfect, but the accuracy cannot be determined. Excellent. You cannot determine neither precision or accuracy. No, that's false, right? So the answer is M. I hope that helps for the final.